Okay, my friends, sorry about that delay. So we're doing redox reactions, the entire chapter, and if I could just take you to a very simple redox reaction. This is a single replacement reaction in which zinc is reacting with hydrogen ions, makes hydrogen gas and zinc ions. I would expect, I know it's been a long time since we've done redox, but this should come right back to you. This is a redox reaction. And would you be able to come up with a description of this reaction in terms of the flow of electrons? From what to what are the electrons flowing? Is what? From the hydrogen to the zinc.
Whoa.
I've had this class now for the third time today. Every hour, they've gotten it backwards, and so you're in good company. It's actually the opposite. And I know why you're making that mistake. Everybody else makes the same mistake. But we have to remember electrons are negative particles. So when something goes down in oxidation number, it's because it's gaining electrons. It's gaining electrons. So the hydrogen's oxidation number is going from 1 down to 0 because it gained electrons. And the zinc is going up from 0 up to positive 2 because it lost those negative particles. You see what I'm saying? So be careful with that. The zinc is losing electrons. It's oxidizing. Remember, when the oxidation number goes up, that's oxidation. That's where we get the word reduction. When the oxidation number goes down, it reduces. The reduction is the gain of electrons. So we have a reaction up here in which zinc is losing 2 electrons, and those 2 electrons are going to 2 hydrogen ions. It's gaining those, and they're making neutral hydrogen atoms, and then they bond together and make H2, and off they go. They'll bubble away. So that's one thing that we're going to have to get used to, knowing, remembering what the definitions of oxidation and reduction are, and being able to describe a reaction in terms of the flow of electrons. Now, if I could, just before we get into that setup, if we were to observe this reaction, the most common expression of the reaction would include a beaker that has hydrogen ions in it. So I'll put some hydrogen ions in there. And then we would have a bar of zinc. There's my zinc. Now, on direct contact, the zinc is willing to get rid of electrons. The hydrogen is very willing to take those electrons. So when the hydrogen runs into the zinc, there's an exchange of the electrons. The hydrogen would grab onto the electrons from the zinc. And we would see bubbles coming off of the piece of zinc. You'd have solid zinc. In fact, it's such a vigorous reaction that the zinc would actually be moving around because there's so much bubbling going on. It's not that the zinc is alive. And it's not even that the zinc is moving on its own power or on its own will. It's the hydrogen that's reacting with it, that's kind of pushing it around, the fact that it's bubbling. That's what the reaction will look like when we have a direct contact between the two. We could also capture the flow of electrons. So the zinc would be giving electrons to the hydrogen in this case on direct contact. The next slide that I just showed you and took off again has the same reaction happening, but it's happening in 2 different compartments that are connected by a wire. Because a wire is a conductive material that can allow electrons to transfer through it. A metal wire is. So if you notice this, we have a bar of zinc, that's our one reactant, and we have hydrogen ions in another container. And these two containers are connected by a wire. This wire over here is attached to a platinum bar. I'll talk about why platinum and where platinum comes from at a later time, probably on Monday. But when we set the reaction up like this, now we can have the electrons flowing from the zinc into the hydrogen through a wire. And if we capture that flow of charge, when you have charged particles that are flowing, they actually are able to do some work. And what kind of work? They can maybe light up a light bulb. They can produce a sound. They could heat something up. We can actually, this is the flow of electricity, essentially. It's just the moving electrons from the thing that's oxidizing to the thing that's reducing over here. And we would see bubbling, instead of bubbling on the zinc now, the electrons are coming into here, and the bubbling would happen on the platinum, where the electrons come in, the hydrogen migrates over there, grabs onto it, and then bubbles away. So it's the same reaction, but this time it's separated by the wire. And if we hook something up to that wire, we can make use of that flow of electrons. So this concept takes us to what the title of the chapter is, Electrochemistry. It's a chemical reaction that is going to now produce electricity if we can take advantage of that flow of electrons and do it through a wire. It's got to be redox chemistry because the electrons have to flow. Precipitation reactions wouldn't help us. Acid-base neutralization reaction, you can't really capture any moving electrons because the electrons stay put. Everything keeps their charges with those kinds of reactions. But when you have a transfer of electrons is when, so redox is really handy for that. Now the way that this picture is drawn, you can kind of see how the zinc is trying to oxidize, it gets rid of those electrons, the hydrogen's trying to reduce, so as they come into here, the hydrogen grabs on and reduces. However, the way it's drawn, if I hold a voltmeter up to this and try to measure like how much current is flowing, it would read 0. There's something missing in this picture that causes this thing to not work at all. I mean, this would be a complete and utter dud. When I ask you to make a battery, and we're going to be doing that in this chapter, you're going to try to make a battery with as much voltage as possible. And if you set this thing up, and I put the voltmeter on and it reads 0, you have no current at all, and that's not good for your grade. You need to at least create some current, or some voltage. So what are we missing in this thing? It looks like it would work fine. Well, here's what's missing. I have it on the next slide. There's got to be something in the middle that we call a salt bridge, and I'm going to show you why on the previous slide. If the electrons are flowing out of the zinc, that means that the zinc is going to be going from the neutral condition to an ion. Since it's losing its electrons, it's going to become the zinc ion, like that. The zinc ion is not going to stay in the metal bar. The metal bar is made up of neutral zinc atoms. As soon as zinc becomes an ion, this bar is going to start to get smaller, and it really essentially is going to dissolve, because it's what happens when metal atoms become ions, is the metal bar dissolves. And the zinc concentration then in this solution goes up, because the zinc atoms are becoming zinc ion. So what's happening in this side is there's a buildup of positive ions, and positive charge builds up. Nature does not tend to build up positive charge, at least in a solution it doesn't. There are some times, and we know this in the wintertime when the air is dry, you can shuffle your feet on the floor and your body can build up positive charge, but it's not stable. As soon as you touch something, it's attached to the ground. Zzz, you know, you get shocked, they get shocked, and you release that buildup of charge. But it is not at all possible in a solution for charged things to build up. You don't ever have a container with overall positive charge. It's always neutral. Always. A solution. So, yeah, the zinc would build up positive charge. And over here, the electrons would come in, and the hydrogen ions would grab onto them, and so the hydrogens would get reduced and bubble out, and this would build up negative charge, because the hydrogen ions would be leaving, and there would just be negative ions left. And so you can't build up charge. So that's why we would need something that we call a salt bridge. A salt bridge is, it describes it down here, it's something that would be contained both in the oxidation half and the reduction half. And it would have, it's called a salt bridge, literally, because it has to have some ionic compound in it, an ionic solution. So as the zinc loses its electrons, becomes ions, it becomes positive ions in here. The negative ions in the salt bridge would migrate in. Nature just knows to do this. And over here, as the hydrogen leaves and bubbles out, we're losing positive ions here. The positive ions from the salt bridge would move into there to keep both beakers neutral. So to get the electrons to flow, and so you won't get a voltage unless the salt bridge is there. You can't allow charges to build up in either container. So what is a salt bridge made of? What does it look like? Well, you can take a crude salt bridge and it would work if you just take a piece of paper towel and soak it in salt water. Literally, you just have to have an electrolyte solution. We remember what electrolytes are. They're ionic compounds that have something dissolved in them. Soak the paper towel in and just put the ends of the paper towel, kind of drape it over so that part of the paper towel is in this and part of it is in this one, and that would provide for a salt bridge. That would work. You can definitely use that in your battery that you create. Another option for a salt bridge, we've been using these for a long time, is this thing. And this is kind of funny because back before there was the internet, we had these things. This is called a U-tube. That's what it is. It's a U-tube because it's shaped like a U. And so what you do is you would take a saltwater solution or sodium sulfate or whatever and fill it up with a solution of it. And then you'd plug both ends of it and put it upside down and into one side into that container and one side in that container. And as long as the open ends are submerged, the solution just stays in there. And so as the current flows, the negatives are flowing into here to keep those positives from building a positive charge. And the positives would go over there to to replace the positives, the hydrogens that were lost. So yeah, you could use a U-tube.